All right, we're going to start the 11.5 video here in the book, just because I can't draw these pictures very well on my own. So in 11.5, we're going to be looking at areas and then lengths in polar coordinates. And we've seen this a lot so far. We did areas and volumes back in chapter 6. We did arc length back in chapter 6. We've done areas and lengths a little bit earlier in this section when we were looking at parametric equations. Same kind of thing now, but now we're just going to be doing areas and lengths here in polar coordinates. So usually I would draw all this stuff out and write it all out, but I'm just going to kind of talk through it here in the book itself. So if we're looking at a polar equation, which is the blue line here in this graph, it would be nice if we could find the area between the origin and that graph for these curves through space and polar coordinates. To do that, we're going to do the same thing that we always are going to do, and that's going to be to partition the independent variable. The independent variable in this case is going to be the thetas. So what we're going to do is we're going to partition up our thetas into chunks, and then we're going to map out the area between these tiny little angles that we're doing. And you can see that we get like these, I don't know what the best thing to call these kind of triangle-ish looking shapes. And all we're going to do is just take the area of each of these tiny little triangles, add them all up, and then take the number of partitions to go to infinity like we always do. So if we're looking at a triangle, this is going to be the area of each of the individual triangles, just that 1/2. And then this is the height, and then this one's going to be like the total distance or the base kind of a thing. And there's a little bit more to it than that, because we don't really want to think of these as triangles. We want to think of these as what we call sectors of a circle. So these aren't even going to be flat at the end. Once we really dive into it, they're going to be kind of curved here in space. So this is the area of a sector, 1/2 r squared, and then theta, the angle of the sector. Okay. And then we're just going to do what we always do. We're going to take each one of these sectors, and then as the number of partitions goes to infinity, and then we get this as our formula. So let's write this back over in our space. The area under a polar equation. And here's our formula. So it's the integral. This is going to be the integral of the angle thetas. So I don't know the best way to do it. I'll just do the way the book does it. It's going from the angle alpha to the angle beta over the function f, which is a function of theta d theta. But it's not just that, right? It's going to be that sector formula. So 1/2 my function squared. Okay. And a little bit different way of writing this, because we don't usually think of this as f of theta. We usually have that written as just the r value. So maybe a little bit better way of thinking about this. Still going to be the integral from the angle alpha, if I can spell alpha, to the angle beta. And then just doing 1/2 r squared d theta. And just remember that r is a function of theta. So there's thetas inside of the r's there. Okay, cool. So we're just going to jump right into an example. I'm going to go back over to the book here. The example we're going to do is this first example here, where we're finding the area inside of this cardioid shape. And so, good, we're just going to go ahead and do it. Find the area in the cardioid. And the equation of that cardioid that we were doing over there is this, r equals 2, 1 plus cosine of theta. Great. Okay, so all we have to do is basically just plug the r into the formula here. So we're going to be doing the integral. I think the hardest part of these questions is determining the angles that you are integrating through. So if I go back over to the picture here with this cardioid, I'm going to be integrating, think about it as the unit circle, from the angle 0, which is going to be going along the positive x-axis, all the way across to the angle 2 pi, which is back where we started. That's going to sweep across my entire picture here to get the entire area. So we're going to be integrating from 0 up to 2 pi. All right, and then we're integrating over 1/2 my function 2 times 1 plus cosine of theta, all squared d theta. Okay, and then we just do that. So to do this, we're going to have to square out the parentheses here. This is a 2 that's squared, so it's really 4 times the 2, sorry, not 4 times 2, 4 times the 1/2, which is 2. So I'm just going to go ahead and bring that out to the front. Still integrating from 0 to 2 pi. And then multiplying that out, we're going to get 1 times 1 plus 2 cosine theta, and then that's going to be plus cosine squared of theta. Come on. There we go. Great. And then still d theta at the right end. Okay, and then we just do each of these separately. Think about this as 3 separate integrals. 1, we can obviously anti-differentiate. 2, cosine theta is pretty easy to anti-differentiate as well. This one, we're going to have to use one of our tricks going back to chapter 8. Remember, whenever you have an even exponent on a cosine or a sine, that's when you want to do that trig identity. So just copying stuff down. We're still going from 0 to 2 pi. I'll go ahead and leave the 1 and the plus 2 cosine theta in there. Okay. Plus cosine squared. Remember, with even exponents, we're going to change it using that identity. This we're going to change to be 1 plus cosine of 2 theta, all divided by 2. Still with the d theta at the very end. Okay. And now we can just put each of these under the 2 and then combine stuff together. So we still have the 2 out in front, still have the integral from 0 to 2 pi. We're going to have a 1 plus 1/2, so we have a 3/2. We still have that 2 cosine theta, and now we're also going to have a plus 1/2 cosine of 2 theta. D theta. All right, now we can do each of these antiderivatives. Still have the 2. Let's do that special little thing that I can do now. This thing. So we still have the 2, and then inside that we have 3/2, which antiderivative of 3/2 is going to be 3/2 theta. And then it's going to be plus 2 sine theta, the antiderivative of 2 cosine theta. This one you got to be a little bit careful about. We're going to divide that 2, which is going to be a 1/4. And then the antiderivative of cosine is sine, and then we still have the 2 theta on the inside. Great. And then we're going to evaluate this between 0 and 2 pi. Okay, so just plugging the stuff into there, still have the 2 out in front. If I plug 2 pi into my antiderivative, it's going to be 3/2 times 2 pi, which is 3 pi. Plus sine of 2 pi is 0, plus this is going to be sine of 4 pi, which is still 0. Okay, so that's going to be minus the 2 that's still out in front, and then plugging 0 into all of this stuff, I'm going to get 0, sine of 0 is 0, sine of 0 is 0. So all in all, we get 6 pi. So remember, the whole purpose of this is that we were trying to find the area in that cardioid. If I go back to the book here, this was the cardioid. The area inside this cardioid has an area of 6 pi. Just to double check that we got the right answer here, there's the book's answer. Okay, cool. So I'm probably going to stop this video here, and then we'll make a part 2 when we start getting into the length of curves.